We have a wire being pushed through a magnetic field at a constant speed. We're given details about the total length of the wire, as well as the length of the height of the magnetic field. We're given its velocity vector as well, right? 2.7 meters per second to the right. We're also given the magnetic field strength. So I'm just going to label the symbols for these quantities. So speed is V, length of wire, well, that's usually L, but we'll hold off on that for a second. Magnetic field strength is B, and width of magnetic field, we don't have a symbol for that either, so hold on to those. Part A, clearly mark the positive end of the wire on the diagram above. So when we move a current carrying conductor, such as a wire, through a magnetic field, right, it's moving, it will induce a voltage. What that means is it pushes the charges. So in reality, it's the electrons that are moving, but we could think about it as pushing the positive charges to one side and negative charges to the other. But we need to work out which direction that is. So to do that, we use the right hand slap rule, or you might have learnt Fleming's left hand law, but I'm going to use the right hand slap rule. So that's, do I dare draw? 1, 2, 3, 4. Oh, look at this beautiful thumb. Oh my god, my hand looks just like this. And here's the palm. Oh my goodness. Anyway, so our thumb and our fingers are perpendicular, and then our palm, in this case, is coming out of the page. Right, so this is right hand. Right hand. And what we want to do, so there's right hand grip rule for a few things. What we're doing is we are following a positive charge. So just imagine a single positive charge right in the middle. It is moving to the right. So our thumb points in the direction of positive charge motion. So get your right hand out. Make sure it's your right one, not your left. Our thumb is pointing to the right. Cool. Now our fingers, which are perpendicular to our thumb, point in the direction of the magnetic field. Magnetic field direction. And we're shown the direction of that by the dots. So dots, or dots with circles, mean out of the page. Whereas if they were crosses, that would be into the page. So in this case, the magnetic field is out of the page. So while your thumb is pointing right, point the rest of your fingers towards you, right, out of the page. And what direction does your palm point? Well, for me, it points down, which means this positive charge is going to be pushed down, leaving the positive end of the wire to be at the bottom. Once more, imagine a positive charge in the middle. It's moving to the right, so our thumb points in the direction of positive charge movement. The rest of our fingers, out straight, they point out of the page. And then our palm is now pointing down. So the positive charges are pushed down, leaving the bottom of the wire positively charged. Alternatively, the top would be negatively charged, right? And that works too. So if it was a negative charge, instead of our thumb pointing right, we point in the opposite direction. So that's left, fingers out of the page, palm is pointing up, so it's pushing the negative charges up. But I usually do the positive charge because it's conventional and you don't need to flip your hand around. Alright, part A done. Clearly marked it with a plus sign. What's next? Part B, calculate the voltage induced in the wire. Right, so like we just said, when we move a wire or current carrying conductor through a magnetic field, a voltage will be induced. as long as it's not parallel to the field. So in this case it's perpendicular, so that's great. Looking at your formula booklet, the induced voltage is the field strength times the speed times L. Now what is this L? Well, you might say length. Great. We have two lengths. It is the length of the wire inside the magnetic field. So they were pretty mean in that they gave you the length of the wire that extends outside the field as well, but we only want the length of the wire inside the magnetic field. So that's 14.3 centimeters. Right, and everything else is given. So magnetic field strength, 1.2 milliteslas, so times 10 to the negative 3. Speed, given in SI units already, and length, 14.3 centimeters, so as meters, that's times 10 to the negative 2. Now we can compute that, so using brackets, 1.2 times 10 to the negative 3, bracket times bracket 2.7, bracket times bracket 14.3 times 10 to the negative 2, closed bracket, gives 4.6332 times 10 to the negative 4. Now looking at the data that we're given, the lowest number of significant figures is 2, right, from the field strength. So we'll leave our answer in 2 significant figures. So that's 4.6 times 10 to the negative, what was it? Negative 4 volts. Negative 4, yeah. So that is the induced voltage, right? Keeping in mind that the positive side is down here and the negative side is at the top. And guess what? That was an excellence question. Right, it was excellence because there were a few prefixes like milli and centi, as well as the fact that you had to use the correct length. Yeah, and the question we just did before, that was achieved. Alright, we got tired and we stopped moving the wire. It is now stationary, but it's connected to a circuit, right, with a battery, 12 volts, and a resistor, 3.4 ohms. Calculate the magnetic force on the wire. So notice it's still inside a magnetic field, right, denoted by the dot, so coming out of the page. A current carrying conductor, so something with current flowing through it, experiences a force inside a magnetic field. Right, and why that's the case is because moving electrons, right, or charge, so current, creates a magnetic field around the wire by the right-hand grip rule, and that interacts with this external magnetic field, causing this force. Right, just like when you bring two bar magnets together, you can feel the force of attraction or repulsion. Here, there's magnetic fields being generated by the wire, and that's interacting with the field that already exists, denoted by those black dots. So calculate the magnetic force. So looking at our formula book, the Lorentz force, right, or the magnetic force, F equals B times I times L. B, magnetic field strength, that's given. Length of the wire inside the magnetic field, also given. Current, not given, but we are given a voltage and a resistance, so we can find that. So let's do that first. So using Ohm's law, current is voltage divided by resistance. 12 volts across 3.4 ohms gives 3.53 amps. Right, because the wire itself has no resistance. That's what we're assuming. Sometimes they might say that the wire has a resistance of like 0.1 ohms. It's usually quite low. So now we know there's current of 3.53 amps. We can now use F equals BIL, where the magnetic field strength is from the previous question, 1.2 times 10 to the negative 3. Current, 3.53. And length, just like before, it's the length of the wire inside the field, which is 0.143 meters. Right, this section right here. And computing that, it gives 6.06 times 10 to the negative 4. Again, mark scheme's not correct. It should be rounded to 2 sig fig, because the magnetic field strength is 2 sig fig. So what is that? 6.0 times 10 to the negative 4, and the units for force are in newtons. Cool. So far this is a merit question. However, combined with the next question, it is excellence. So we've worked out the magnitude of the force, but now we need to consider the direction. So they've given us a few options. So current is flowing from top to bottom. How do I know that? Well, the positive terminal of the battery is where conventional current flows, right? Positive current. So current is flowing down. Magnetic field is out of the page. So using your right hand, we point our thumb. So thumb goes for the current, which is down. Then our fingers, the rest of them, point in the direction of the magnetic field, which in this case is out of the page. So thumb down, fingers out of the page, and our palm is pointing in the direction of the force. In this case, that would be left. All right, so try it with your right hand. Thumb goes down, fingers come out of the page, and our palm is pointing left. So left. All right, and with that and the previous calculation, that is an excellence. All right, an electron cutting the magnetic field experiences a force and follows a circular path. Okay, so linking to circular motion. Clearly mark on the diagram the direction it moves around the circle. So two options, right? Is it going clockwise or counterclockwise? So we're going to need to use the right hand slap rule. So let's have a think. So thumb, fingers, and palm. Now the thumb, instead of thinking of the electron, let's just think of a positive charge for a second. It's a little bit easier. So positive charge. So our thumb points in the motion of positive charge. Right, and so the electron would obviously have the opposite motion. So our thumb points in the direction of the positive charge. Now, we don't know what that direction is. So that's what we need to find out. So let's orientate our fingers and palm first, and wherever our thumb is pointing will be this direction of the positive charge. So where do our fingers point? In the direction of the magnetic field, which in this case is out of the page. Now where does our palm point? Well, recall palm is the direction of the force. So what's the force going on here? It's the force keeping the electron in a circular motion. And we know from circular motion That's called the centripetal force, and it is acting inwards, right, in to the center of the circle. So palm is into center of circle. Now, that seems a bit confusing because there's lots of points where it's into the center. So let's just pick this point right at the top. So from that point, our fingers point out of the page and our palm points down, right? Into the center is down. So which way is your thumb pointing? So fingers out of the page, palm points down because that's to the center. My thumb is pointing right. And so that would be the motion of a positive charge. Now, just, extra for experts, let's do the point down here. So again, fingers out of the page, palm is now pointing up, right, to the center. Palm is pointing up. Where does your thumb point? Well, it points to the left. So that is the motion of a positive charge. So what's the motion of an electron? The opposite direction. In other words, it will be going counterclockwise. So get rid of those red arrows, and there is our motion of the electron. And so this question is a two-part question, so let's go on to the second part to explain why there is a force on the electron as it cuts through the magnetic field. So what's giving rise to this force and hence this circular motion? So electron, or rather moving electron, which is basically another word for current, right? Current is the movement of electrons per second, or charges per second. So the moving electron, or the current, creates a magnetic field. Now, there is an existing magnetic field, right? Those black dots coming out of the page. So this interacts with the existing magnetic field. Now this interaction creates a strong and weak side, like relative to the electron. So a strong and a weak side of the magnetic field. And the electron moves into the weak side. Think of it like a hill. If we add together the fields, the electron is going to want to naturally go towards the weaker field, right, further down the hill. So the electron moves to the area with a weaker magnetic field. And these 4 bullet points in conjunction with this anti-clockwise arrow would be an excellence. Cool. Now, just to sort of illustrate these last 2 points, I'll just do a side example, but I mean, this concludes, the video in terms of looking at the past exam. So just a side example, if it lets me get to the side. So let's have a wire with current flowing down. Now, using the right hand grip rule, wait, before that, getting ahead of myself. It's inside of a magnetic field, and let's say that magnetic field is going into the page. Alright, denoted by the crosses. Now let's use the right hand slap rule to determine the direction of the force acting on this wire. So thumb points down in the direction of current, fingers into the page, direction of the field, my palm points right, so it experiences a force to the right. Cool, so orientate your hand so you get that. Thumb down, fingers into the page, palm points right. Cool, so we know the force is to the right. Now, let's draw the field produced by the current. So using right hand grip rule, thumb points down, our fingers curl around the wire. So on the left side, they're going into the page, and on the right side, they're coming out of the page, like so. And you'll notice on the left, they're in the same direction, so they're adding together. On the right, they're in opposite directions, so they will subtract, and we're left with a weaker field on the right and a stronger field on the left. And so the force pushes the wire towards the weak side from the strong side. And this argument can be made not only just for a wire, but like we just saw in the question, with a single particle, right? But it's a bit harder to draw because its motion is constantly changing, which is why I use the wire as an example. All right, that's it from me. Time for some lunch. See ya.